To solve this problem, we must analyze the rich geometric relationships embedded within a semicircle. A fundamental property of circle geometry states that any angle inscribed in a semicircle that subtends the diameter is a right angle. Consequently, triangle ABC is a right-angled triangle with its right angle situated at vertex C. When the segment CP is drawn perpendicular to the diameter AB, it serves as the altitude to the hypotenuse of this right triangle. This altitude splits the primary triangle into two smaller subtriangles, triangle ACP and triangle CBP, both of which are fundamentally similar to each other and to the overarching triangle ABC. The path to finding the radius relies on breaking the diameter AB into two distinct segments, AP and PB. We can begin our calculation by isolating the smaller right-angled triangle on the right, triangle CBP. Because we are given the length of the altitude, CP equals 8, and the hypotenuse of this subtriangle, BC equals 16, the Pythagorean theorem allows us to directly compute the length of the base segment, PB. Evaluating BC squared minus CP squared reveals that PB equals the square root of 192, which simplifies beautifully to 8 times the square root of 3. With the first segment of the diameter established, we can invoke the geometric mean theorem, also known as the right triangle altitude theorem. This theorem dictates that the square of the altitude drawn from the right angle is equal to the product of the two segments it creates on the hypotenuse, yielding the algebraic relationship CP squared equals AP times PB. By substituting our known value of CP and our newly discovered value for PB, we can isolate and solve for the remaining segment, AP. This calculation shows that AP is equal to 64 divided by 8 times the square root of 3, which rationalizes smoothly to 8 times the square root of 3 divided by 3. The final phase of the solution requires aggregating these components to find the total length of the hypotenuse, which represents the full diameter of the semicircle. By adding the lengths of the two segments, AP plus PB, we find a total diameter of 32 times the square root of 3 divided by 3. Because the radius of a circle is defined precisely as half of its diameter, we divide this final sum by 2. Through this systematic application of similarity and right triangle trigonometry, we find that the exact radius of the semicircle is 16 times the square root of 3 divided by 3, or approximately 9.24.